I didn't mean to close that. Now, one reason I said that and brought it up to you is that Thursday's class is out there now, okay? And, all right. Name, please?
Roger McKinney.
Okay. You must have just added.
That's it.
Okay. And what's the last name again? Brookin?
McKinney.
Oh, McKinney.
Yes, sir.
Okay. Kinney?
Yes, sir.
MC?
Mm-hmm.
Okay. And first name was?
Roger.
Roger.
Yes, sir.
Is that what you go by?
Yes, sir.
Okay.
Just call me Rod.
Which?
Rod.
Rod?
R-O-D. Rod.
Rod.
For short. Yeah.
Okay, so yours was Roger with a D.
Roderick. R-O-D.
Oh, Roderick.
Yes,
Okay,
sir.
got it. Okay.
Yeah. You just call me Rod.
Okay. I'm hard of hearing, so, okay. Good to have you here. Okay. Now, I was just saying this, so I'll start over a little bit. What I'm doing, and right now we're recording, all my not being able to hear is recorded on it. And this is a package called Screencast-O-Matic, and when class is over, I'll upload it to YouTube. It usually takes an hour or two, maybe longer sometimes if the system's slow, for it to upload. But the bad news is for me to move it to the playlist so you can access it easily. I'll explain that in just a second, okay? So let me go over, so the point of that is you can see and hear last time's class, last Thursday's class. It's out there now, okay? So let me tell you how to get there. And over the weekend, I did finally get most things caught up. I'm still missing one class. I've got to do some upgrade to it, but I couldn't do it at home because I didn't have the books I needed. So what's out there now, are y'all all familiar with Blackboard? Yes? Okay, good. If you go to Blackboard in this class, they changed Blackboard recently, updated to a new thing, or we have anyway. And somewhere when you go to this class, there's a column, and at least on the instructor side, they're blue tabs, okay? I don't know what it is on the student side. I don't get to see the student side. But they're blue tabs here. I think they're blue. And the old ones were. Yeah, I'm pretty sure they are. It's somewhere down there it says My Syllabus, okay? The syllabus is out there, and it's updated. And there are a couple changes from what you'll hear if you watch that first class or listen to the first class, and you who are here for the first class, here are some of the changes that are on there. Before I wasn't sure if the linear algebra class was going to make or not. It looks like it will, and some of you are in that, okay? So I don't have an hour class period free. So my Tuesdays and Thursdays I get here usually a little before 7:45, unless traffic is bad or something like that. So a little before 7:45 until 8 o'clock. There's big 15 minutes of office hours, right? Then I have this class from 8 to 9:50, a big 10-minute break before my linear algebra class, 10 to 11:50, another big 10-minute break until my physical science class, which is 12 to 1:50, but then it has a lab with it, so from 2 to 3:30, I have a lab, and then at 3:30, I book it away from this campus, head to the Birmingham East campus, and teach a 4 o'clock physics class. Okay, so it's kind of crazy. I don't have but 2 10-minute periods, office hours in between classes, 15 minutes at the beginning and 30 minutes near the end, but I've got to be driving those 30 minutes to hit to the other campus. And then I do have, and this was not on the thing before, I will be over there. That class ends at 5:30. I'll stay there till 6. So there's my biggest office hours on Tuesday and Thursday, 5:30 to 6, but it's over on the Birmingham East campus in the nursing building, which is Ethel Hall building, and it's K103, I believe, is the room number on that campus. So I'm not very accessible here Tuesdays and Thursdays. Okay, now what did change, and I was thinking I might lose a physics class. I actually lost 2 physics classes. So on Mondays and Wednesdays, I have an 8 o'clock class, Calculus 1, because that's a 4-hour class. It goes until 10:40, because we're a 10-week term. And so I have a big 20 minutes between that class and my next class, which is Cal 2, 11 to 1:40. And then after 1:40, or I'll say 1:45, I'm free until 6. So there's my biggest chunks of office hours, 1:45 till 6 on Mondays and Wednesdays. Okay? Now Fridays, we have, the school is open this Friday. It was last Friday. It's open this Friday, but then it will be closed all the Fridays, the rest of the Fridays in June and July. Then in August, we're open again, but there's only like 1 Friday left in the term then. So, but when the school's open, like this Friday, I'll be over on the Birmingham West campus, and my office hours are in the several places. They're in the syllabus, and they're also in the locator card. So you can see that. But those Fridays are only good this Friday and that 1 Friday in August. Okay. Also, this class requires a research paper. We went over that last time, right? Yeah. Okay. It's out there. You can listen to what I have to say about it on the YouTube video, and you can read it because it's in Blackboard too. So let me show you where the rest. The syllabus is under my syllabus. Now there's a whole string of those blue tabs here, and somewhere it's not near the bottom, but it's usually the bottom of my screen, first screen. It says something really bizarre like course handouts and more. I don't know who came up with these tabs, but it sounds really good. My syllabus and course handouts and more. That course handouts are not really handouts, but other things. That's the only logical place I could find to put it. Used to be one tab that said content, and that made sense. Okay, now the content isn't listed. So under content is the research paper instructions, my locator card showing when I'm in class, when I'm out of class, when I'm on campus, off campus, that kind of stuff. Okay? Then, I can't remember what order, but I have this book does not come with PowerPoint, so there's no PowerPoints I can put there. But what I could put there are some websites that either I've discovered or other students have discovered and said they found useful for the course. Okay? So those links are there. Now, some of those are linked to this text, but they're not linked to the new edition of the text. They're linked to the previous edition. But there's very little change usually between editions. Okay? So you can find additional help on those sites. And then I think the last thing listed is Math 238 YouTube videos. And that's this class videos. So that's where you can go and find last Thursday's class and see and hear everything I've talked about. Now, if you're really an astute observer, you'll see the syllabus I'm talking about in the link doesn't look exactly like the syllabus that you'll see under syllabus, okay? And the reason is they came out with a new format, and that's what I was working on over the weekend, is getting everything into the new format and getting the corrections made, because the ones I was talking from before was last fall's syllabus. The content, the major stuff was the same, it's just the dates and stuff. So all that got corrected too. All right, now, there was something I forgot last time. I had just gotten back the day before we had been overseas for about 9 or 10 days. And I think I must have been jet lagged or something because I completely forgot about 3 things. One thing that we have to do and talk about safety. They want us to do this every term. I find it's best to do very early in the term rather than breaking it up in the middle of things. So let's go on and hit that. 3 areas of safety. Can anyone think what they might be? Lauren. All right. We've increased the class size since you were last year. Okay. All right. Anyone think of 3 areas, any one of the 3 areas of safety we might need to think about? We're not going to be doing any chemicals in this class. We're not going to be, doing anything that we would have to have, but just general. Weather, okay? We are in the midst of the first named storm of the season right now. Of course, it's not hitting us badly, but if it was a major hurricane, which you can have, and sometimes those pack such a punch that we still get tropical storm type situations here, which could cause tornadoes and things like that. So we have to think about that. What do we do in case we hear that siren go off? What's the general rule? Yes, go low and interior. Perfect. Okay? Now, how do you get there from here? Here's a diagram of the second floor of this building. We're here in this classroom in the corner. We go out the door and bump into, what's your name? Monica. Got it. Monica Carter, right? Okay. Welcome. I was just going over safety. Look at this. We've got all but one student here. And that's the one student that we left the class open for. I don't know where she is because she was a Lawson student who needed this class to graduate. She pre-registered and now is not here. I've got all you folks here. You can thank her if you ever see her. Otherwise, this class would have been canceled last week. So I'm glad y'all are here. Okay, and hopefully she'll show up. Okay, so we go out the door here, hang a left, go down half a flight of stairs right down there, and then hang an immediate left, go down one more flight, and you are close to being as low as you can go. This building doesn't have a basement, but if you go down that one floor, then go in, don't go out. Don't say, oh, bad weather, I got to get home and let the dog in, or something like that. No, you don't. You don't want to be in the car, the dog will take care of itself. Go interior. Okay, when you go interior, right in front of you, you'll see restrooms. And actually, those are pretty safe places because the greatest strength is in close walls and corners. And the restrooms have both of those. The walls are close and you have lots of corners. And this is where the greatest strength of the building is. Okay? So, but if you don't want to spend the extended length of time in the restroom, that may not be your favorite place. You can go down, it's sort of about 2 or 3 other steps. Immediately on your right there, underneath this is what it's called the corridor here, is the academic dean's office. She's very seldom over here, but when she is, but somebody else, the associate dean sometimes comes over, and then there's a summer program they have, and the guy who heads that up uses her office some. So if anyone's in that office and they will invite you in, that would be a fairly safe place. And here's why these are safe places. This back wall of that is almost like a basement. There's soil behind that. There's no other room back there. It's actually built into the soil, the landscape. Okay? They're built on a hill, so it falls off that way. So that's a pretty good place. But if that's not to your liking, the next room down is a classroom. Now that's a big room. It's a computer. Looks like a computer lab, but it's actually a math classroom. And again, this back wall, very safe. The corners, very safe. And the other walls are pretty strong too. So that would be good. I wouldn't get in the middle of the room unless you had to, because something could fall through there. Right next to that is, you go through glass doors in the hall, and that lets you into the library. The first door on the right in the library, right after you come in, is a little computer room. And that's much smaller than the classroom. So again, closer walls and 4 corners, and the back wall, again, is right up against the floor. Okay? The next room to that is what I call the research room. That's where the globes and the atlases and things like this, you don't check out the books there, but you just use them there. That's okay too. It's a little bit bigger, maybe not as big as the classroom, but still a little bit bigger than the computer lab. But again, that back wall is a very safe wall, and all the walls and corners are pretty good. I wouldn't go any further in the library at all, because then you're exterior. You don't want to be exterior, you want to be interior. Now, all that being said, another safe place, and this is where most people will congregate, is the hallway. Okay? The hallway has close walls, Unfortunately, no corners, but close walls. And the other big advantage to the hallways is it has emergency lighting. The bathroom doesn't, the bathrooms don't, none of those do. If the power goes off and if there was a weather emergency, the likelihood, here she is, I'm sorry, I didn't keep you out. Okay, 100% attendance today, way to go. All right. Keep it up, folks. Jasmine's here. All right. Excellent. Okay. 1, 2, 3, 4, 5, 6, 7. 4, 3, 7, 5. Now, most of the time, we do not allow summer classes with fewer than 10 students. Thank you, Jasmine, for needing this class. That's why it gets to run with only 7. And I hope this is the case, but if it's not, make it the case. Y'all have to be paid too, by the way. And if you haven't paid yet, please pay as soon as possible because they will bump you out and may not let you back in. So please get that done as soon as possible. We're just talking about safety. I've forgotten to do this on Thursday. So that's where you go. Low, first floor, interior. The hallway is pretty good in that it's got emergency lighting. The walls are closed, so you have certain strength there. The restrooms are better strength-wise with no emergency lighting. The dean's office is strength-wise with no emergency lighting. The classrooms, especially that back wall, very good, and the corners are good. But again, no emergency lighting. But don't go into the library where you have external windows, because that's where things can blow in, glass can come in, you could get injured. All right, another thing. When you go down, all of you look pretty healthy today, okay? But it could be some of you could have a skiing accident or something like that and have a bum knee or ankle or something like that and be a little bit slow going down. I will be going with this last person down. So the rest of you are going to get there first, but I will be carrying with me my handy little grade book because once we get down there, we'll all congregate together to begin with, and I'll call roll, make sure everybody made it. And if somebody decided to make a run for home or something like this, and we don't know about it, then somebody has to go back upstairs and risk life or limb in case limbs are coming through windows and stuff, and look for you. Don't do it. Hang together, especially until I get the roll called, and then someone will they'll let us know something, and they'll get us back to normal as soon as possible. The worst place you can be is out in the road. Okay, so there's weather. What's another type of emergency or safety issue we might have? That's external. Fire. Say again, fire, okay? I'm going to lump with that chemical spill, okay? We aren't going to deal with any chemicals. Someone else may, say something in the chiller room here starts emitting a refrigerant that is pretty obnoxious or something like that, and we don't want to be smelling and stuff. But let's say there is something like that happen. What do we do then? Let's start with the worst case scenario. Worst case scenario, my computer explodes, okay? It starts arcing and sparking, setting all the paper on fire, the desk is wood. What do we do in a circumstance like that? Say again? Leave. Okay, good idea. Let's get out of Dodge and leave the rest of the building to worry about it themselves, right? No, we want to warn them too. So what do we need to do before we leave? Leaving is right. Pull the fire alarm. Excellent. Where's the closest fire alarm? I know y'all were checking this out when you came in this morning, weren't you? You wouldn't see any on any of this old hallway here. This is the old part of the building. It was built before fire alarms were required. This is an old building. So nothing close to us will have a fire alarm. So where you have to go, since you have to go a little distance, I would say go in a pair, buddy system. Okay? Go out the door here, hang a left, go down that half flight of stairs again, and go to this little corridor that goes across here. There's the new part of the building that just recently filled this in. It used to be a horseshoe-shaped building. Then they put this part in, then they put this part in. This first floor, so it doesn't show up here. As soon as you go through that corridor, you're on the second floor here, go through that flat corridor, and you're on the first floor. Okay, not a single step there. And you can either turn to the left or to the right, and either place there's a fire alarm within sight. So that's where the fire alarm is, okay? And if the fire started in here, what else might we choose to do rather than just get out of here and let the whole building burn down? Second? Yeah, fire extinguisher. Where's the closest fire extinguisher? Oh, y'all didn't notice that on your way in either, did you? Okay. Right there, 5 feet from where I'm sitting. Okay? Safe, closest you can get on this fire extinguisher. Someone go get that. I know some of you all your life have wanted to break that glass out of you every time. That would be so cool. Probably not, just you guys, probably the only ones. Okay. Okay, so you would go out and get the fire extinguisher. I'll handle it if necessary, okay? In fact, I'll go break the glass if necessary, and then I'll try to do what I can to put out the fire, okay? The rest of you, getting out of Dodge. Now, where do you go for that? Okay, here's the deal here. Go out the door, hang a left, down that half flight of stairs, hang another left. This time you go out. You don't want to go into a burning building. You want to go out of a burning building. And what the old rules used to say, at least 75 feet from the building. Now they say, and here, by the way, is where we are. We're in this corner classroom right up here. And we go out into that parking lot. It's hard to see with all the trees here leafed out. So there's a parking lot right down there. You can see it sort of. And just head out that door and down into the parking lot. And you say, hey, building's on fire, no more school today. In the car, I'm going home. No. Okay? Because you need to account for everybody. Remember, I'm up here putting out the fire if I can. I'm also with the last unit out. If they're a little slow or something, turned an ankle when they got panicked or something like that. So I'm the last one there, carrying my roll book. And when I get out there, y'all stay together in a group. I call roll again. If we can't find you, somebody has to go back into a burning building looking for you. Either a fire professional or one of us. Okay? I don't want anybody to have to do it. Hang together. Someone will be around to let us know what happens. Okay. So there's 2 out of 3. External emergency, weather, flow and interior. Internal emergency, fire and chemical spill, out into the parking lot. Okay? What's the third? Unfortunately, it's in the news way too frequently these days. Active shooter. Never even used to think about something like this. Now, it's unfortunately so commonplace we have to think about it. What do we do in case you hear something that sounds pop, pop like it could be gunfire? Guess what? You have better hearing than I do. I've already told you. I'm hard of hearing. You're going to hear it first. Oh, let's back up a little bit. If that fire started in here, one more thing. Fire alarm, the fire extinguisher, but one more thing we ought to do, because we know it first. Say again? 911. Okay, I kept trying to get the things in the right place there. Okay, 911. Even better than that, if you put the Lawson State Police Department number on speed dial on your phone, do that first. Now, I never bring my phone to class because I don't want it ringing when I'm up here teaching, because I'm going to ignore it anyway. So I leave it down in my office. Today, I left it on charge. I forgot to even pick it up, so I don't even have it. But y'all usually have your phone, someone dial 911. Now, if we hear the fire alarm, obviously, happen somewhere else in the building, then we just get out of Dodge. But if it started here, let's let somebody know first. Okay. So, active shooter, if you hear that go off, if you hear what could be gunfire, what do you think we should do? You tell me. I haven't been through these drills before, huh? Okay. Here's what we do. This door, because a student now, everybody's here, but we don't usually lock the door from the outside. I do have a key for this door, but unfortunately, there's no buttons, there's no keyhole in here. I have to go outside to lock the door. And I will do that, okay? And get it done as quickly as I can with shaking hands and all like that. So I will try to secure this door, and then don't close it until I get back in, by the way. Okay, then I come back in. But unfortunately, there's another entrance to the room. There's this door here, that connects to this office here, that connects to this office here. That opens to that door. the bathroom over there. I don't have a key for that, so I can't lock that door. I do have a key for this one, and this does have buttons on the side. So do we lock it? It's locked from here, but not locked from here. So don't lock this door. He can get in, we can't get out. So don't lock this one. This one has a deadbolt. I don't have a key for that. However, this door, now by the way, if I come and do this, I'm going to close that door anyway. And it looks like there's like 10 here. To close the door, you can't lock it. So this one, if you press this button, it does lock from the outside, not from the inside. Okay? So that's what you do. Lock this door and close it. Close this door. Why? There's glass in that door. He can see in and maybe see somebody in here. So close this so he can't see. It looks vacant. I'm going to close this door again. And close this door just for safety. Okay? Make it look like nobody's here. Okay? So we've got the doors as secure as we can. Now what do y'all do? Right back here. Lauren, and right, yeah, okay, yeah, over here. Because he can shoot through glass, break glass, may even be able to shoot through the wood. Sort of hard to shoot through concrete block. Okay, that's the safe place to be. We turn off the light. We get very quiet. Turn your phones off the ring. We don't want it ringing in at any time. And we just sit here very quietly and wait until we hear. Okay. Sorry we had to go through that. Any questions on that? Okay. All right. That covers the safety issues. Let's get back to math now. Sorry. We got started last time on chapter 1. And I think I may have said something wrong before. 1 is a bigger chapter. I was thinking my linear algebra, not this one. So I said before 1 and 2 was one test, and then after that, there's a test after chapter 1 and a separate test after chapter 2. If you hear that on the syllabus, I was getting it confused. Okay. But last time we got as far, didn't get very far, but we got to page 4, because we went over syllabus and all that kind of stuff. And first day of class, there were people coming in, there were people getting lost, and so there were lots of issues going on. Okay, we got on page 4 now. I don't know if any of you, I don't see any books now. This is the text. I think you can get an ebook for it. I'm not sure. You can rent it. You can do whatever. It's generally a good thing to have. I would not have made it through differential equations without the book I had, because I had a really rotten instructor when I was in college. He was a professor. In fact, his subtitle was Dr. Ray. His nickname was Death Ray. Okay, he was awful. But I had a great text. I don't think this one's as good as that one was, but still the text is helpful. So I highly recommend having it and using it. Last time we were talking about how we talk about differential equations. 3 ways to classify. Okay? Talk about the type, and there's only 2 types, ordinary and partial. In this course, we're basically going to deal only with ordinary differential equations. Those are with derivatives, not partial derivatives. Partial differential equations deal with partial derivatives. We're not going there. Okay? The second classification is order. That's which derivative are we talking about. Every differential equation has to have a derivative in it, or a differential in it somewhere. Okay? And that could be a first derivative, a second derivative, a third derivative. Whatever the maximum derivative is in that equation, that's the order. Okay? And that's what we're picking up today. We had talked about the type. Now we're dealing with order. Okay? Just to bring you up to speed, let me give you the example that they give in the text. Let me get my pen activated for dark. Okay? Yeah. Okay. Now, first, what type of differential equation is this? Remember, there are only two types. Ordinary. Those are derivatives, not partials. Okay? So it's an ordinary differential equation. What order? Okay, ordinary order. They sound alike, but they talk about different things. What order is this? Second. Why? Because of this, that, or this? The first term. That's the second derivative. This is a first derivative squared. That doesn't matter. That's the first derivative. If this hadn't been there, that would be a first order differential equation. But because this is a second derivative, this is a second order ordinary differential equation. Okay. Now, and it refers back to example 1. So let's go back to example 1 just quickly. 1a was dy dx. That's why I wish you had the book. I wouldn't have to write all this down. Plus 5y equal e to the x. Okay? And last example 1 was talking about type. That's a ordinary. Okay? What order? First. Okay? First derivative is the only derivative you see there. Okay, this one, d2y dx squared minus dy dx plus 6y equals 0. Again, ordinary differential equation, not partial, because those are ordinary, they're just regular derivatives. But what's the order? Second. Now notice you don't have to have, these first two happen to have even the same function on the right side of the, and by the way, a differential equation has to have an equal sign. If you had something that looks like that, that's not a differential equation. That's an expression. An equation has to have an equal sign. You may have something to the right of it, or you may only have a 0 to the right of it, but you got to have an equal something. Okay? Now, dx dt plus dy dt equal 2x plus y. Whoa, that's a little different. What's different about that? Two dependent variables. Excellent. Only one independent variable, t. These are both dependent variables. Okay? Still an ordinary differential equation. What order? First, okay? Because both of those are two first derivatives. Okay? The b part here has partials in it. There's no reason to really do that, so let's leave those alone. Okay? But they talk about them, but we won't go there. Here's another way you can express a differential equation. In fact, according to its name, this is sort of a better way to express it. But this is a differential equation. M of xy dx plus n of xy dy is equal to, it could be something else, but usually it's 0. Okay. Wait a minute, that doesn't look like any of these others. What do we call this form? Where we have just a dx or a dy. What do we just call that form? What would you call this? Just that, or just this? That's a derivative. That's a partial derivative. No, it's not partial. That would be that curly thing. Partial would look like this. Okay, so that's not partial. That's the partial. This is a regular d there. But what do we call that? A differential. Remember, when you have the express the derivative like this one right here, now, pure mathematicians cringe at this, and they balk at it. But it's a lot like, but you're not really doing it, if you multiply both things, everything on all sides by dx, that would be dy is equal to 5y dx. dy plus 5y dx equal e to the x dx. You can combine these two together, e to the x minus 5y dx. That's a differential form. This is a derivative form. So actually that is a differential equation because it has differentials in it, okay? But this is also a differential equation. We talked about that last time. Now what does this indicate to you, the way it's written here? Sort of the same thing you just said. This looks like there are two independent variables, okay? But you don't ever see another. So, it's not real clear. Most of the time, y is your dependent and x is independent. But written like this, it looks like m depends on x and y, n depends on x and y, so it looks like they're both independent variables, but really the y depends on x. Because you could, this isn't what you're doing, but write this as m of xy plus n of xy dy dx equals 0. It's a little messier that way, so usually when we have this form, we write it in this manner. That's also a differential equation. And what order is it? First. It is an ordinary differential equation because those are d's, not partials, and these are, none of those are second derivatives. In fact, I can't think of writing those with second derivatives in them. That only works for first derivatives. Okay. So that's also another form, and that's called the differential form of the differential equation, of a linear, shouldn't say that yet, first order ordinary differential equation, written like this, that's called the differential form. So let's do example 2. Okay. If we assume that y is the dependent variable of the first order ordinary differential equation, then recall from calculus that the differential dy is defined as, okay, let me say that again. Okay, y is the dependent variable of a first order ordinary differential equation, okay? Then you would say that dy dx, if x is the dependent variable, is equal to, and another way, now this is nothing magic here, y prime. That's just two ways of expressing the derivative, right? Now that y prime is probably also a function of x. I'm not going to write that in right now, but it is a function of x, okay? Now, to write that in differential form, that would be dy is equal to y prime dx, okay? Now what it looks like you did was multiply both sides by dx. You didn't. Don't ever tell a mathematician that's what you did. That makes them go into anaphylactic shock, I think, to hear something like that. What you just wrote it in differential form, which basically looks like the same thing, okay? But remember what you used to do then? Integrate both sides. You did this when you were doing oh man, not substitution, but some of the other techniques for solving for integrating, techniques of integration. You did something like that. Going blank on integration by parts. Integration by parts. You did exactly this type of thing, but you didn't start with the other. Okay, now, the A part of example 2, it says by dividing by the differential dx in an alternate form of the equation, okay, well they do call it dividing by that, and these are written by mathematicians. I'll back off from what I said before. I guess it won't send them crazy. Y minus x dx plus 4x dy is equal to 0. There is a differential equation in differential form, okay? It's in the D form, not the D by D yet, okay, form. That's a differential form, okay? Now, he actually said do it. So what we're going to do is, just as he said, divide everything by dx. And of course, dividing that by dx isn't going to change anything. So now what you have is nothing here, y minus x plus 4x dy dx is equal to 0. Okay? Now, a little bit of manipulation here, as in rearranging the order and adding x to both sides. And now you have 4x dy dx plus y is equal to x. That is, later we're going to learn, is a standard form for a linear differential equation. And we haven't even talked about linear yet. But we will sometimes manipulate something that looks like that to get it back to a derivative form rather than a differential form. So feel free to multiply or divide by dx's, even though a lot of times mathematicians really hate for you to say that. And the reason I hate for you to say it, this is an operator. That's not a division. But if you go back to the limit that came from, that was a division. Okay? So you can do it. It's legal to do. They just usually don't like you to use that terminology, but he did. Okay? All right. Let's start with a different differential equation. This is the B part of example 2. Okay? Six xy dy dx, can't write, plus x squared plus y squared equals 0. Okay? Now, you don't know this yet. Okay? No reason for you to know this yet. That would be a really difficult differential equation to solve in this form. So guess what they say? Go to the differential form. How would that read? You tell me. Write that in differential form. Excellent. If you multiply every term on every side by dx, and since these two are together, I'm going to do those by dx once and this by dx. Okay? Then what we'll have is the dx's go out here, and you have 6xy dy plus x squared plus y squared dx is equal to 0, because 0 times dx is still 0. Okay? Believe it or not, this one has a better chance of being solved than that. Okay? Whereas on the last example, the derivative form is easier to solve than the differential form. Okay? So, feel free to go back and forth to get them. Now, to me, this first chapter is kind of nebulous. We're not really solving. I'm not giving you anything to do. It's all nomenclature, at least this first part of it. But these are techniques that you can put in your tool belt and pull them out whenever you need them. Okay? You just don't know when you'll need them. Okay, we'll get there later. Okay, now, they're going to write it in sort of a symbolic form here. This is an nth order. We're talking about order now. To me, this book kind of wanders. All this is supposed to be talking about order, but that last example had very little to do with order at all. Okay? Now they're getting to it. Here's a way to write an nth order ordinary differential equation. And rather than writing all those words, that's ODE. That doesn't mean I'm going to start quoting some poetry and singing to you. That's not that kind of ode. This is ordinary differential equation. Okay? In one dependent variable, and that happens to be x here, here's a way to write that. Some function f, capital F, of the independent variable x, the dependent variable y, and then y prime, y double prime, dot, 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 up to the nth order, the nth different derivative of y. And that's equal to 0. Okay? That's how we sometimes express in generic form a differential equation, an nth order differential equation, meaning it goes up to the nth derivative, and it can have all these other terms in it, pluses, minuses, multiplied, divided, blah, blah, all this kind of stuff. But you have to have your independent variable, your dependent variable, and all your derivatives. Now, some of those could be 0, okay? Now, your independent variable better not be 0 because that's not an independent variable. It's a fixed variable. But some of these others could be 0, okay? But that is a generic way to express an nth order ordinary differential equation, okay? Because your primes indicate derivatives, not particles, okay? And you'll see that form a lot, okay? Now, the deal is, how many variables do you have in that? I want to say no, you're right. Okay, if you just look at derivatives, the first derivative, second derivative, up to nth derivative, that's n terms right there, right? Plus the 0th derivative, the variable itself, plus the independent variable. So n plus 2 terms. That function has n plus 2 terms in it, potentially, okay? And therefore, when you're dealing with those, later we'll talk about conditions, initial conditions, boundary conditions, those kinds of things. You're going to have a lot of conditions to be able to solve that exactly. But we'll get there later. Okay. Now, tell me a different way to write the nth derivative of y, with x being your independent variable. You might be familiar with the term, the Leibniz notation. What would that be? Maybe you're not familiar with the term. It has d's in it. How would you express that in d notation? That's sort of a weird way to say it. D n y over dxn. That would be your nth derivative, right? Okay. So, with that in mind, we could write this differential equation, okay, solve for this, because there's a 0 over on the right-hand side. So we could, whatever that equation is, we could say d2y dx dny dx to the n is equal to some other function, let's call it little f, and that would be of x, y, y prime, y double prime, dot, 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 up to, and how far would this go? If you pulled out the y to the n on the right-hand side, or left-hand side, what would you be left with, the maximum term here? The n minus first derivative. So you could take that form, solve for your y to the n, and this one would be, yeah, you may have some fractions, you may have other things, but it could be written as some function x, y, and all your derivatives up to the n minus first derivative, because you got the nth derivative over here, so you got that. So there's another way, generically, to refer to a a nth order differential equation. Okay? Now, this they refer to as the normal form, okay, of this, okay? And I don't know why. That's not perpendicular, so that's not what the normal mean. It's just like, I don't know if you remember back in when you're solving equations with more than one unknown, and you had ax plus by equals c. They called that the standard form for a linear equation in two variables, but it really wasn't a very useful form. It wasn't a handy form. You'd much rather have that as like slope-intercept form, y is equal to mx plus b. That told you a lot more than that. So I don't know why they call that the normal form. Maybe you'll see some reason later. I can't imagine it now. So let's go on to example 3. Okay. And again, I don't like these early sections, but they're necessary to get the nomenclature down. Okay, example 3, the A part. Here's what they're giving you. 4x dy dx plus y equal x. There's a first order ordinary differential equation. Now, that's not quite in what they call normal form yet. What's keeping it from being in normal form? Say again? No, okay, yeah, you're right there. Well, remember, the normal form had equal everything else on that side. The equal x is okay. You need the y over there, and you also need to get rid of the 4x. Okay? So that would make it in normal form. I don't know if that's what that is what they're gunning for. So let's solve for the highest order that you've got, this one, and let's do that. Okay? So let's first subtract y from both sides, and that would give you 4x dy dx is equal, because that adds a 0, x minus y. Okay? And then divide by 4x, because you don't want that there either. Okay? So that gets rid of that. So now you have dy dx is equal to, now I'm going to monkey around with this a little bit. That's a perfectly legitimate form you could have, or you could say 1 over 4 minus y over 4x. There's another perfectly legitimate form that you could do. This is just as good as that, but realize they can write it different ways. Okay? This is what they're calling the normal form. Okay? I don't see anything much that looks too normal about it, but that's what they're calling a normal form. Okay? Now, in this circumstance, I'm kind of glad they you don't have a book, because I have an error in it. I haven't found many, but here's one I have found. Here is another differential equation. Y double prime minus y prime plus 6 equals 0. Okay? Now, what would be the normal form of that? What would you do? What you did here was isolate the maximum derivative you have. What would you do there? Isolate the maximum derivative you have. Okay, what kind of differential equation is that? It's what? Second order ordinary differential equation. Exactly. So what's the maximum order? 2. So isolate that second derivative. We'll add y prime to both sides and subtract 6 from both sides. Okay? And that gives us y double prime is equal to, those add to 0, y prime minus 6. Now what they have in the book is y prime minus 6y. Totally wrong, okay? There's no y up there. So either you needed a y up there to make this true, or you don't need the y down here to make that true. I don't know which way they were gunning for. It really doesn't matter. It was just an example. And not asking you to solve it or anything. But that's one reason I said, I'm glad you didn't have the book to confuse you here. So I'm going to go with the simpler form and just erase the y. Okay, what you had to begin with was correct. Okay, so we've talked about the type of differential equation, two types, ordinary and partial. In this course, we're only dealing with ordinary, okay, mostly, okay. Then the order of the differential equation is what the maximum derivative in that equation is, okay? And then what they're calling a normal form, which I really see very little use for, is when you isolate the maximum derivative and have everything else on the other side. Okay. Now we're going to talk about classification by linearity. What do we mean by linearity anyway? And by the way, there's only two types of this too. There's multiple orders. Two types of differential equation, ordinary and partial. Any number of order, maximum derivative. But when you talk about classification by linearity, there are only two possibilities. Okay? And those are linear, and guess what the other is? Nonlinear, okay? That's all we're worrying with now, okay? Okay, linear or nonlinear, okay? So, an nth order ordinary differential equation, remember that was the one they were calling for, the capital F, the blah, 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 is said to be linear, okay? So here's your, I'll write it down again because you don't have your book. Nth order ODE, that was your capital F of x, y, y prime, tell me what to put next. Y double prime, dot, 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 y to the n. By the way, let me, we talked about this last time, but most of you weren't here last time. Okay. When you're talking about a higher order derivative, that's when you put the parentheses in there. You wouldn't say a fourth order and you say y to the fourth. That indicates it's y raised to the fourth power. Y with the 4 in parentheses, that means it's the fourth derivative of y with respect to your independent variable. Okay, there's your nth order ordinary differential equation. Okay, now that equation is linear if and only if this. All the parts with the y, not the x's, okay, but all the parts with the y can only be to the first power or the zeroth power. In other words, they're not there or they're or to the first power. If you had a y squared in there, a y to the 3/2 power, a square root of y, anything other than y to the first power is not a linear. And if you had the first derivative squared, remember those early example like that, the fifth derivative to the 3/2 power, not a linear equation. Every one of your y's and its derivatives would only be to the first power. That's where the powers come in. Okay, linear or nonlinear. That means that the nth order ordinary differential equation is linear when, and here's how we're going to write this down. This is another way to express it. A to the n of x, dny dx to the n, plus a to the n minus 1 of x, dn minus 1 of y, dx to the n minus 1, plus, this is tedious, n minus 2 x, that's a derivative, not a partial, dn minus 2 y dx to the n minus 2 plus dot 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 plus a sub 0 of x times y. Now they actually put one more in here. Let me put it into plus a sub 1 of x dy dx. Okay. Your dot, dot, dot connected all that. This is the other way of expressing that f. It's not that f, because the f, remember, I left off a very important part of it. That f is equal to 0. Okay. So this isn't the same, but you can express it this way. So if you took your nth derivative, it may or may not have a coefficient function, not just a coefficient. Now the n here is just an indicator, just a counter. That says this is the function that is the coefficient function for the nth derivative. Okay, nth derivative, that n is important. That's how many derivatives it is. This says this is just the coefficient function that goes with that. So this n is a marker, you might say. This is the one that goes with that. 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 First power, first n. And this is the 0th power of the 0th derivative, which is just y, and that would have the a sub 0 here. And then you can have any function of x you wanted to over there. Okay? So again, this is a ordinary differential equation, because all these d's are d's, okay? This is nth order because the maximum derivative is n, nth derivative. Now this is linear because every one of these derivatives and the y itself is to the first power. That's what makes it linear. If any one of those was squared or cubed or 1/2 power or 3/2 power or 7/9 power or whatever else, no, not linear anymore. Does this g of x have to be linear? No, it can be anything. E to the x, we saw several of those. Not linear. Doesn't have to be. It could be, but it doesn't have to be. Do these a sub x's have to be linear? No. They can have any power of x. Fractional power, transcendental function, doesn't matter. Okay? It's the y's and the derivative of y's that can only be to the first power. That's what makes a linear function. What makes it nonlinear? Any one of those is not. It's a nonlinear function. Okay. Now, let's talk about two special cases, the ones we're going to use most of the time. And this will be linear first order and linear second order. A sub 1 of x dy dx is equal to g of x. Oh, wait, I'm sorry. It can have a sub 0 of x, y is equal to g of x. Okay? There is a linear, because none of your y's are raised to any power, okay, or derivatives of y. First order, ordinary differential equation. Only derivative there is a derivative, not a partial. Okay? So this is often called, let me clean that up because it's ugly. Okay. Okay. So there is one form, one expression of a linear first order ordinary differential equation. That's the generic form for it. Okay? Second order would be a sub 2 of x d2y dx squared plus a sub 1 of x dy dx plus a sub 0 of x y equal g of x. And the g of x can be anything. The a of x's can be anything. They don't have to be linear. They can be anything. It's the y's that have to be linear. Okay? That's your linear second order ordinary differential equation. Okay. Okay, so what are the keys? the dependent variable y and all its derivatives must only be to the first power. Okay? The coefficients, a sub 0, a sub 1, a sub 2, a sub 3, a sub n, of those coefficients depend at most on the independent variable x. Now here's the other thing I didn't explicitly say, but it's in here. Well, this is say a1 of x, or a2 of x, or a0 of x, okay? That means this is the only variable it has. You can't sneak a y in here and have it as a function of x and y. Not allowed. That won't be linear then, okay? So the coefficient functions are functions of x alone, and your right-hand side is a function of x alone. No y's can be over there either. It may not be linear if it has a y over there. Okay. So a nonlinear ordinary differential equation is one that is not linear. Okay, pretty clear, huh? Okay. It would have something that would knock it out of being linear. So let's see if we can do example 4. Here are two equations. By the way, y'all have to help me keep up with time. I get carried away, so don't let me run over, because I have another class starting in 10 minutes, and some of you are in that. How many of you are in both classes? 1, 2. Just 2 of you, okay. All right. Here is an equation. Y minus x dx, oh, they write it in differential form even, plus 4x dy equals 0. Okay? Now, my question to you is, what type of differential equation is that? All we're doing is ordinary. What order of differential equation is that? First. Okay. Then the third, is that linear or nonlinear? You know, looking at this form, I can't quite tell. Okay? So what might you have to do to clear that up for you? Yeah, divide by dx. Got it. Okay? Okay? And this would then be y minus x y minus x plus 4x dy dx is equal to 0. Okay? Can you tell now whether that's linear or not? Yes, it is. Now, it may not quite look like it. Let's just rearrange it slightly. In fact, I think we've done this one before, haven't we? Very close to it. Since I lost the dx there, it divided out, I don't really need the parentheses anymore. Don't need that blob there anymore either. Okay? And you have 4x dy dx, that's that term, plus y is equal to x. Sure enough, that's linear. This is first power, that's first power. These also happen to be first power, but that doesn't matter with a linear function. The x's can be anything you wanted them to be. It's the y's that matter, and the derivatives of y. So that is a linear first order ordinary differential equation. Okay, how about this one? Y double prime, going back to our prime notation, minus 2y trying to see if that's a misprint or not. It doesn't say. It's silly the way they've written it. Plus y is equal to 0. Okay? Is that linear or not? It's ordinary. Prime notation indicate you don't use prime notation if you had partials. Remember, you use that subscript notation if you had partials. Okay? So that's not a partial. That has to be ordinary. What order? Second order. Now the question, linear or not linear? It's what? Not linear? Why not? No, 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 no. You can have linear nth order. Remember we had that out there. Linear or not? It is linear. Now the way they've written it here, that could be simplified as y double prime minus 2 minus y is equal to 0. I don't know why. I have a guess, and it's just a guess. I have nothing to base it on, except it just looks dumb written this way, that this was supposed to be a prime there. Okay? But whether it was a prime there or not, those would both be linear equations. I can't imagine why they'd write minus 2y plus y. I mean, that's sort of dumb. But what if it had been this? Y double prime minus 2y times y is equal to 0. Non-linear, because that would be minus 2y squared. The y term is not first power. It would now be non-linear. Okay, very good. I couldn't trip you up. Okay, I tried, but I couldn't. X cubed d3y dx cubed plus x dy dx minus 5y is equal to e to the x. They love that e to the x, don't they? Okay. What can you tell me about that differential equation? First, what's its type? Ordinary. Those are all d's, none of them are partial. Good. Okay. What's its order? Third order. Maximum derivative is a third derivative. And is it linear or nonlinear? Linear. But wait a minute, that's x cubed is not linear. Doesn't matter. The x functions can be anything they want to. The e to the x is not linear. That doesn't matter. That doesn't. It's only the y's and the powers of y and the derivatives of y. Y to the first, y prime to the first, y triple prime to the first. And then your third order ordinary differential equation. Good deal. Okay? Let me clear the screen so we can do another. All right. 1 minus y prime plus 2y equal e to the x. Now here's another thing they didn't address in the first part, and I forgot to mention it as well. Okay? Can any of you look at that and tell me whether it's linear or nonlinear? And I apologize for not saying it before. Okay? Now, looking at that, you don't see a y or a derivative with any exponent other than 1. But there's one other thing they forgot to mention, and I forgot to mention it too. You cannot have a cross term. You cannot have a product of a y. See, a y times a y would be y squared, and a y prime times y prime would be y prime squared. But neither can you have a y prime times a y. You can have it added to a y, subtracted from a y, but not multiplied, and even divided by a y. So this is nonlinear. Why? Because if you write this out, this would be y prime minus y times y prime. No, you can have a function of x times y prime. You cannot have a function of y. They actually did say it, now that I think about it, because remember they said the coefficients have to be functions of x alone. This coefficient would have a y. So yeah, this is not a linear function, because that coefficient is not of x alone, it's y. That part is okay, that part's okay. This part is not, because it has a what I call a cross product of a y and a derivative of y, or two different derivatives of y, not a linear function. They didn't spell that out, and I forgot to say it. d2y dx squared plus sine y is equal to 0. Linear or nonlinear? Okay. Sine is not a linear function. If that was sine x, perfectly fine. Sine y, not perfectly fine. That's sine y is not a linear function of y. It's curved all over the place, okay? Not a linear function of y. If that had been an x, that would be linear. With that being a y, dot linear. It can only be y's to power, not some function of y, y to the first power, or y double prime to the first power. Okay? And how about this one? d4y dx to the fourth plus y squared equals 0. Linear or nonlinear? Nonlinear, because that is not a exponent of 1. Okay? It has to be linear in all the y's in the derivative. If that had been an x squared, that's linear. No problem. So y squared, no. XY squared, no. Okay. All right, good deal. Now, y'all, most of you weren't here last time, and there was a thing on page 2 that said one of the goals in this course is to solve or find solutions of differential equations. So far, we've just been naming them, classifying them, that kind of stuff. We haven't even come close to solving one, okay? So, here is a definition of the concept of the solution of a ordinary differential equation. So, I apologize ahead of time. My writing stinks. That's why I wish you had books so I wouldn't have to even write it, okay? Any function phi, defined, now abbreviate like crazy, on an interval I, okay? In the future, I'm going to put that as an element of I, okay? On an interval I, and possessing, okay, at least n derivatives, I'm going to abbreviate derivatives, and I abbreviate it wrong, that's a V, okay, that are continuous on I, okay, which, this is a wordy sentence, which, when substituted into an nth order differential equation, again, I don't like, DE means differential equation, okay? Nth order differential equation reduces the equation, that's equation, to an identity, okay? It's said to be a solution. Of the equation on the interval. Okay. Now, I hate to say this, but to me this almost seems like a worthless definition, doesn't it? It doesn't say how you find that solution. It just says if there is a solution of any function that when you take those n derivatives of that, first that the n derivatives are continuous. If they weren't continuous, that's not going to work, okay? But when you take that Take those derivatives, put it back into the differential equations you had, ordinary differential equation, then you get an identity. Then that's said to be a solution. Okay? But it's important because if it doesn't work, that's not going to be a solution. And what we're going to be doing, we're going to find some things, and some of them will look like they're a solution. But remember when you're doing word problems, and you love those in elementary grades and stuff, and the teacher usually would say, plug it back in and see if it works. Okay? That's what you have to do here. If you come up with something you think is a solution, you got to take it through and show that it is. If it doesn't come up with an identity at the end, even though all the steps indicated it might be, if it doesn't actually produce a solution, it's not. Okay? So, again, that tell you how to find the solutions, just tells you characteristics of it. Okay. In other words, remember our good old capital F notation? The capital F acting on x and y is this function. Phi of x, phi prime of x, phi double prime of x, dot, 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 all the way up to phi nth derivative of phi of x. It must be 0. Okay? If y is equal to phi of x is a solution, then when you plugged in those phis and all those derivatives of phi, you better be able to get a 0 out of it. Okay? And that should work for every x on the interval. Remember, when it says define on an interval I, that interval I is on your horizontal axis. It's your x. It's your independent variable there. Everywhere on that. So this must be true for every x in that interval for it's defined. If there's some place in there where one of these is not defined, no, you can't do it. Okay? So this will be for all x in the interval I. Now, that's how I'm going to do it, so I don't have to write in the interval. Okay? All x is the element of that interval I. We say that phi satisfies the differential equation on I. That's another way of saying it. For our purposes, we shall also assume that a solution phi is a real valued function. Now, what do we mean by that? We're not going up into complex space. I mean, we're not going to have any imaginary parts to it. We're going to leave it. Later, we're going to have to incorporate some imaginary things to our thinking, but we're always going to get them back to real valued functions. Okay? So we'll have to deal with some i's at some point, but they won't be part of our solutions. Okay. So I don't know if most of you weren't here, so you would. But if you were here, you may have remembered we started with an equation like that. Okay. Started with a differential equation here. dy dx is equal to 0.2xy. What type of differential equation? Oh, is that a differential equation? Yes. What type? Only time we do. Ordinary. Okay? What order? First. Linear or nonlinear? Second, linear. It is. Because this is to the first power, your y is to the first. It has a coefficient, but that coefficient has x's on it. Okay. So, now, what they claim, without telling you how they did it, that y is equal to e, and we did this before, e to the 0.1 x squared. Okay? They claim that is a solution, okay, of that differential equation. How would you verify or check or argue whether it is or not? Take the derivatives. Good answer. Okay? So y, or let me go and write it, dy dx, I can't write it, okay, is equal to, take the derivative of that. Anybody? Oh, e is my favorite function to take the derivative of. What's its derivative? Itself. So that's going to be e to the 0.1 x squared. But in this case, you also have taking the derivative of the, yes, the chain rule. You have a 0.2x, right? In front, chain rule. Derivative of the exponent, right? Okay? Now, notice this part right here is exactly your y, and that's exactly 0.2x times y. Yeah, that is. That does produce an identity. This thing is equal to that thing. Yeah. You take the derivative, you find that to be the case. Didn't look like it here until you realize this is exactly your y. Okay. So sure, that is a solution. Okay. And guess what? That is good on the interval, all real numbers. Any x possible, because e is defined everywhere, its derivative is defined everywhere, no restrictions at all. Occasionally it will be convenient to denote a solution by an alternate symbol, y of x. And in fact, in my mind, why did they even introduce the phi of x in the beginning with? I would have called it y of x to begin with and had it all done. But they threw in the phi of x, which maybe later that'll make more sense. Okay, now let's talk about that interval. That was sort of a strange thing in here. You cannot think of the solution of an ordinary differential equation without simultaneously thinking the interval over which that's true. That's going to be something true of differential equations because if you have some place where, say, a derivative is not defined or some higher order derivative is not defined, or maybe even the function itself is not defined, you can't have an answer that covers that, you might call it singularity, the place where it's not defined. So you have to define it on some interval on which that does have a derivative or whatever. Okay. The interval and this definition that I have here on the top of the screen here is various called the interval of definition, the interval of existence, the interval of validity, the domain of the solution. All those mean the same thing. Or can be just an open interval AB or a closed interval AB. What is the difference between open interval and closed interval? Open interval AB, closed interval AB. What's the difference in those two? Yes, okay. This means it's every value between A and B, but not necessarily at A or B. This will mean every value between A and B, including both A and B. And you can have mix match too. You can have an open here and a closed there, closed here and an open there. Yeah, but usually we are going to deal with either open or closed. And most of the time, it's not going to be a huge difference. Just every now and then, there'll be something that can't be defined on one end or another, or both. Okay. Now, the other thing, either the A or the B could be an infinity too. So you could have something that's A to infinity. But infinities always are closed out by a parentheses, because infinity is not a number. So you can't include it. It's not a number. So most of the time we'll make the A also open. But it doesn't have to be. All right. Let's go to example 5. Okay. Verify that the indicated function is a solution of the given differential equation on the interval minus infinity to infinity. Okay? So here's the differential equation. dy dx is equal to xy to the 1/2. Okay, there's your differential equation. Here is the proposed solution. Y is equal to 1/16 x to the 4th. Now you need to verify that that is a solution. So what would you do? Take a derivative. Very good, because you're trying to find out what dy dx is. So find out what dy dx is. And what would that be? Oh, wait, this is Cal 1. I'm already through with Cal 1. I don't need to know that stuff anymore. No, sure you do. What's the derivative? 1/4 x cubed. Is that what you said? Okay, good. All right. Everybody agree with that? Now, frankly, to me, that doesn't look much like that, does it? Well, another thing you need to know before you can get that, what is, I don't know what to do, what is y to the 1/2? If y is equal to this, what's y to the 1/2? 1/4 x squared. Now, let's see if, indeed, dy dx, which we've just said is going to be 1/4 x cubed, is that equal to x times 1/4 x squared? Sure, of course it is. So, yeah. dy dx, 1/4 x cubed, is equal to x times y to the 1/2. Just had to do one other little step there, figure out what y to the 1/2 is. And that was pretty easy in this case. Okay? Now, what type of differential equation was this? Ordinary. What order? First. Linear or nonlinear? Non-linear, because that you can't have a y to the 1/2 power. X could be the 1/2 power, but not y. So this was a non-linear, by the way. Okay? Where was it? Okay, here. Let's do the B one here. Here's your y double prime minus 2y prime plus y equals 0. Okay? By the way, let's start with this. What type? What type? Ordinary. What order? Second. Linear or nonlinear? Linear. Perfect. Okay? So, let's see if this is a solution or not. Y is equal to x e to the x. Okay. Is that a solution? Well, what's one thing you got to do? Second, take a derivative. Y prime sits there in prime notation. Let's do it in this. And what would that be? Oh boy. Second, e to the x. Okay, I buy that. Is that all? What else? Long time ago, wasn't it, for Cal 1? E to the x plus, what are we using here? Product rule. Okay, and I take it that you did the derivative of the first times the second. That gives you e to the x. And then what do we do? First times the derivative of the second, which would be x e to the x. Right? All right, we got that one done. Felt like pulling teeth, but we did it. Okay? And what else do we need to do? Help me. Y double prime is e to the x plus Same thing as we had before, isn't it? E to the x plus x e to the x. So we can simplify that a little bit by saying 2 e to the x plus x e to the x. Right? All right. So let's plug and chug here. Y double prime we said was 2 e to the x plus x e to the x minus 2 times y prime. So that'd be minus 2 e to the x minus 2x e to the x. And I skipped a step there. Is that okay? Y'all are all right with it? I didn't put the 2 outside the... You okay with that? You want to see all the steps? See what I did? It wasn't magic. It was just, I was lazy. Plus y. And what's your y? What is your y? X e to the x. Okay? Now let's see what happens if we start adding these together. Here's a 2 e to the x minus 2 e to the x. Okay, that adds a 0. Here's a x e to the x plus x e to the x. That's 2x e to the x minus 2x e to the x. That's 0. And 0, sure enough, is equal to 0. So sure enough, there is a solution to that linear second order ordinary differential equation. Make sense? All right, good deal. Now they go through some other stuff. On this second one here, is that the only? I guess what we could say, what's the interval for those, for both of those? Oh, they already told us, didn't they? Yeah, it's supposed to be good for all x's. Okay? The only thing that gives me a little pause is that y's can't be negative. But guess what? This definition of y says it's never negative, because for any value x, it's always going to be positive. So that's okay. And this one here, not going to matter either. Okay? So I think that's going to be good everywhere. Now, especially in the second one, where this was your ordinary differential equation, I can give you another solution, and it's actually embedded in that too. Y is equal to 0. Because what's the derivative of 0? And the second derivative is 0. So 0 plus 2 times 0, or minus 2 times 0 plus 0 is 0. That's called the trivial solution. And anytime we have, and we're going to later call this an homogeneous equation, it's equal to 0, the trivial solution is, I want to say, always going to work on that. I believe that's going to be the case. Okay? So, they mention it now because you'll run into it later. A solution of a differential equation that is identically 0 on the interval I is said to be a trivial solution. Sometimes that may be our only one, but that is a trivial solution. All right, now, they go back to the phis, and that's the same as the y, whatever you want to call it, okay? The graph of a solution phi of an ordinary differential equation is called a solution curve. Now, I think that all of you could graph that one with no problem. I mean, that's just a parabola-looking thing with a very small coefficient. So that's pretty easy. This one would be a little more challenging, but it still works pretty nicely. That basically is going to be a when x equals 0, y is equal to 0, so 0, 0 is going to be on it. And then anything to the right of here, you have your envelope sort of is your y is equal to x, and then the exponential function is multiplied by that. So that's going up like this. Over here, your x is negative. E to the x is still positive, but then this is that makes the whole thing negative. But e to the x is approaching 0 real quickly. So that wouldn't be particularly easy to do, but you could draw the graph of it. Now, so that's the solution curve. They didn't do one for you, but I was trying to just wave my arms on that one. Let's do example 6, which will involve the curve on, oh wait, I'm sorry. Yuck. Okay. What if we had, this is a function, y is equal to 1 over x, okay? What's its domain? This doesn't look like a differential equation, but it sort of is, okay? It's not a differential equation, but we need to be able to think back this way. This is way back in probably pre-calculus. What's the domain of that? It's all the values that x could be. That's the domain. Is there any value x can't be? 0. But all other x's it could be. So the domain of that function is all real numbers except x cannot equal 0, right? Now, if you were to draw a graph of that, without getting too picky about it, okay, what would that look like? Basically, a hyperbola, like that. Probably not that ugly, but you get the general idea. All real numbers except x equals 0. X equals 0, y is undefined. Okay. So, if we wound up with that being a solution to a differential equation, what could be your interval? Or what couldn't be your interval? Remember, the interval is the values for x's. So the interval, the maximum interval you could have would either be minus infinity to 0, not counting 0, or 0 to infinity, not counting 0. You could not have a bracket on either one of those zeros because it's not defined there. Anything else, like 1 to 3, negative 7 to negative 2, anything like that, perfectly fine. But you could not have a 0 in there. Negative 1 to 1, no. No, no. You cannot have that 0 anywhere in the interval. So this could be a legitimate solution anywhere, this interval, anything that's contained in that interval, like negative 7 and negative 2. This interval, anything contained in that, like 1 to 3. Anything there would be legitimate intervals, but you could not have negative 0.5 to 3. No, that contains a discontinuity. Can't do it. Okay. Now, I'd hoped to get this one finished, but I don't think we can. We're going to start next time with the B part. Okay? And y'all don't have your book, so you don't know that. So this is on page 7 in your text, bottom of the page, the B part. Next time we'll have the full time to do differential equation. We won't have any more preliminary stuff to do. Are you planning to get books or not? What's your plans? E-book or rent a book, or, there's several options you have. But if you do get the book and I suggest that you try to, on your homework exercises in section 1.1, I think the books all have odd answers in the back. I have to check because I don't want to, yeah, odd answers in the back. Any of the odds 1 through 7, number 9, 11 or 13 or both, 15 or 17 or both, 19 looks like a doozy, but try it if you can. 20 or 21 or both, 25 or 27 or both. And then you can stop there. We'll pick up the rest of those later. All right, get it. That's on pages 12 and 13. Now, if any of you want to find an earlier edition, this is 11th edition. Earlier editions are a lot cheaper, probably, and very little changes between editions. So it may not be the same page numbers, it may not be the same problem numbers, but you can live with that too, I think. The only reason they change editions is that the publisher can make more money, because the publisher doesn't make money selling used books. So they make the authors change the colors, change a little bit here or there, and come up with a new edition. So I'm sort of not too big a fan of the publishing industry. All right, any questions? Good deal. We'll see you on Thursday. What's that? Oh, and it's on the syllabus and everything, but you can, if you need to get the ISBN, there it is. Or turn it over, whatever you need. Okay. All right, good deal. Thanks.